to be reviewing some set theory for you, and then I'm going to be on paper doing some scalar collections. Again, the point of this, the point of almost everything we're doing right now, is to put you in a good position to analyze the two pieces you're going to be analyzing for your final project. And because you're choosing your own pieces, and those pieces are so diverse in genre and what have you, we need a lot of different tools. So we had our chromatic harmony tools. We reviewed those the other day, and today we're going to review set theory, which is also a very it's a useful tool for dealing with pitch material, for talking about pitch materials, for talking about intervallic relationships in a wide variety of pieces. It can be used to some extent in almost any piece, and it can be used to really great extent in certain kinds of music. And of course, that depends on the context. So the sort of first notion that you have to change when you're thinking about set theory, we're used to thinking about pitches. But when we're doing set theory, we're actually talking about pitch classes. We're no longer talking about pitches. We're talking about pitch classes, which is just to say there are only 12 pitch classes: C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, and B. And all of their enharmonic equivalents, or their octave equivalents, are a part of these 12 numbered possibilities. So every C sharp, no matter where it is on the staff, we call 1. And every G sharp we call 8. Okay. And if we have an A flat, we call that 8 too. So there's something called octave equivalence, which means octaves are equivalent, they're the same, they don't matter. And enharmonic equivalence, which means B sharp and C natural are considered the same. That's a really different thing than when we were talking about tonal harmony, right? If you're in C major and you see a C sharp, that's probably a part of a secondary dominant tonicizing the 2, tonicizing D. If you're in C major and you see a D flat, that's probably a Neapolitan, part of a Neapolitan. So C sharp and D flat really do mean different things in a tonal context. And that's why set theory more or less isn't particularly useful in a tonal context, or is of limited use. But in a lot of other music, it is. So here are pitch class numbers, 0 through 11. Sometimes we do T or E for 10 and 11 just to sort of make it clear that we're writing 10 and not 1, 0. Right? And then, as you remember, we sometimes write these on a clock face from 0 to 11, going around the clock. And this allows distances to be easier to spot. So if we're talking about the distance between, say, C and F, a perfect fourth, we can see very easily on the clock that it's shorter to go from C to F than it is to go from F to C. And we're always going clockwise around the clock. This also, the clock face allows us to see certain types of symmetry. This comes up in composers like Bartók and Debussy, but also some atonal composers like Webern or Schoenberg. If you mark certain pitch collections on the clock, you will actually, the symmetry will be pictorially shown. You know, an easy example is like the whole tone scale is every other number, right? 0, 2, 4, 6, 8, 10, 0. And so you can see, for instance, the fact that that divides our octave equally, that it maps onto itself. Similarly, if you do a fully diminished chord, 0, 3, 6, 9, you're hitting each sort of north, south, east, west point of the clock. And that's reflecting something about the symmetrical nature of the fully diminished chord that's related to the reason. That's the reason why we can respell it, reinterpret it. We can start on this note and treat that as the root, or we can start on this note and treat that as the root. And we can sort of see pictorially why that works on the clock face. So it's a nice tool. There are two types of, we call them transformations, you can make in set theory. You can transpose and you can invert. And we use T for transpose, and we use I for invert. And so if we have some pitch classes here, 4, 9, 1, 2, and we transpose them by 3, you write it like this, T3. And when you're transposing, you're just adding that number to your pitch class. 4 becomes 7 because it's 4 plus 3. 9 plus 3 equals 12, which is the same as 0. 3 plus 1 is 4. 3 plus 2 is 5. And so you get this T3 transformation of your original, transposing up 3 half steps. And so this is something you can, a way you can talk about any transposition, even in a tonal context. Right? That if we think about, Beethoven, bum 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 bum, da 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 dee. Well, those are different intervals. One's a major third, one's a minor third. But we could refer to the transposition as down 2 half steps, so it would be like T minus 2. Right? And that might just be an easier way to label on a score the transposition of a motive. Even if it's not a piece that particularly lends itself to set theory, you can use it just to be a little sort of neater about your notation of motivic transformations. Inversion, as you remember, I'm sure, you subtract the number from 12. So you do 12 minus whatever you're inverting, and that gives you the inversion. So if we again have 4, 9, 1, 2 as our, this is just a random set of pitch classes. We do 12 minus 4, 12 minus 9, 12 minus 1, 12 minus 2, and we get 8, 3, 11, 10. That's our inversion. And you can see originally we had bum, beam, up a perfect fourth, down a sixth, up a step. Now this is down a fourth, up a sixth, down a step. So it's the same intervallic content flipped. This was a perfect fourth going up, now it's a perfect fourth going down. Right. And when we're doing this type of inversion, we're inverting around 0 or 12. We're inverting around 12. So if you imagine C, a C natural here. Actually, let me do this. Let me bring this, I'm just going to pop this up here. So 4, and let me see if I can put a little dot. 4, 9, 1, 2. Here's 4, 9, 1, 2. Nope. Now I'm going to draw a line through the 0 pole. And I'm going to have another dot for my inversion, which was 8, 3, 11, 10. So there's 8, 3, 11, 10. As you can see, the gray intervals, pitch classes rather, have been flipped around this axis of 0 or 12. See, we've inverted them. And you can see it here visually on the clock face. These two have sort of flipped over here. This one is flipped over here, and this one is flipped over here. See that? So that's what we're doing when we invert. And if you have a combination like this, where you have a transposition T2I and an inversion, you always invert first. You do the inversion first, and then you do the addition. And that's just going to be shifting this inversion around the clock face. Right. So usually when we're doing set theory, the sort of goal is to find the prime form. Okay, and the prime form is that sort of lowest common denominator of the intervallic content of some group of pitch classes that we can then use to refer to any transformation of that prime form. So we have a prime form, and that allows us to say, here's the prime form, it's been transposed. Here's the prime form, it's been inverted. Here's the prime form, it's been transposed and inverted in this way. And this is sort of the main tool of set theory. It's the prime form. And there are 3 steps we take to find the prime form of any given set of pitches or pitch classes. The first step is to find the normal order. Then we find the best normal order. And then we find the prime form. We put everything in brackets except prime forms. We put in parentheses to show how special they are. So, first step is normal order. You start with some pitches in some music. Here's some music. Beautiful. First thing you can do is remove duplicates. Because remember, this E flat and this E flat are treated the same in set theory. Octave equivalents, same thing. This C and this C are the same. So there's really just these 4 different pitch classes. And then we're going to arrange them from low to high in 1 octave. And of course, you can start on any one of these. It doesn't matter where you start. You're just putting them in some ascending order. And then rotating it so that we get every version of this pitch collection, this pitch class collection, in ascending order, starting on C, starting on E flat, starting on G, starting on B. Okay. Then to find the normal order, we want the smallest interval between the first and last note. We want the most condensed version of this ascending set of pitch classes. So this one is like a major 7th. This one is a major 6th, that's smaller. This one's a minor 6th, so that's even smaller. And this one is also a minor 6th. So these two are equally small. So one of these is going to be our normal order. If you have a tie, and you won't always have a tie, you have to go to this other step, which is to say, which is the most scrunched to the left? This is how I like to say it. Some other people, as you can see, this is talking about the rightmost interval. Scrunched to the left is the rule I like. You'll see this one starts with a major 3rd, this one starts with a minor 2nd, this one is more scrunched to the left, which means this is our normal order. So we want the smallest distance between the first and last pitch when we put them in ascending order, and we want it the most scrunched to the left. Smallest intervals on the left side, bigger intervals on the right side. And so this one ends up being our normal order, B, C, E flat, G. Okay? That's our first step. The second step is basically to say, we found our normal order. If we invert our normal order, is it even more scrunched to the left? That's basically the question. Okay. So here's a new set of pitches. We remove the duplicates, so it's just 3 pitches. We find the normal order, which in this case is E, G, A flat. That's the most small distance we can make between these 3 pitches, okay, when we rotate them. Then we invert it to find the best normal order. So we do the 12 minus, and we get 8, 5, 4. Again, I could bring this fella out. Right. Here's our original set is E, G, A flat, 4, 7, 8. 4, 7, 8. That's our original set. We're inverting it, and we end up with 8, 5, 4. Eight, 5. Oops, sorry. 1, 2, 3, 4, 5, 6, 7, 8. Right? So these 3 have been flipped across this axis of 12 or 0 and inverted. See that? You can see the symmetry. This is not a bad way to check your work. So we found the inversion, 8, 5, 4, and then we basically do what we did before to find the normal order. We take those numbers, we stack them in all the ways we can, and we find the most scrunched to the left and smallest version of our inverted version. So we had E, G, A flat before. Now when we inverted it, we can get E, F, A flat as our most scrunched and to the left normal order. And then we compare our 2 normal orders, the normal order of the original pitches, the normal order of the inverted set, and we see which one's more scrunched to the left. And in this case, the inverted version it starts with the half note. So we needed to invert this in order to find the best normal order. Okay? And then the third step is we take that best normal order and we transpose it to 0. We 0 it out. And then we give it that name starting on 0. So in this case, E, F to A flat. We transpose it down to 0, so we get 0, 1, 4, C, C sharp, E, and our prime form is then 0, 1, 4. Okay? And that gives us the sort of purest, most reduced version of that intervallic content, 0, 1, 4. And then when we refer, if we see in the piece at a later point music like this, we can say this is really 0, 1, 4. Even though it's been inverted and it's been transposed, it's related to 0, 1, 4. Okay? All right, so that is your recap of prime form. I'm going to switch to paper now and do some scalar collections. Symmetrical, scalar collections. Scalar collections in general, but particularly some of the symmetrical versions that we see in a lot of 20th century Western music. We, of course, are very familiar with our major and minor scales. We also have, of course, our pentatonic modes. And, of course, there are many, many, many different pentatonic scales. The 2 we learn in this class are these major and minor pentatonic modes. Do, re, mi, sol, la, do, and do, me, fa, so, te, do. Sorry, my dog is woofing at some passersby. Then, of course, we have the diatonic modes. That's your, oops, Ionian, Dorian, Phrygian, Lydian, Mixolydian, Aeolian, and Locrian. We should all be familiar with those. And these are all just scalar collections. And then we get to symmetrical scalar collections. One of these is the chromatic scale. Or the chromatic collection. And this might seem to be a totally useless scale because it's just like every pitch or whatever. So, and for the most part it is, but there are times when it's worth noting that a composer is using every pitch available and not in a way like 12-tone music does, which is a very principled, very sort of rule-based way. But Bartók, for example, will sometimes use all 12 pitches in a set. You'll get sort of motivic elements like this in Bartók. This is not a real example. This is just me sort of imagining some Bartók. He likes these kind of snaky melodies. With whole steps, half steps. So if you saw a measure like this, you could notice C, C sharp, D, E flat, E natural, F, F sharp, G, G sharp, A, B flat, B natural, C. Oops, I didn't notice I went so far away. So if you saw an excerpt like this in Bartók, it looks a little like something you might see in an excerpt. You might notice that this is making use of what we might call the chromatic collection. Now, it's not in any particularly principled way. I just sort of wrote these snaky little melodies that you might see in Bartók, where there's a lot of minor thirds and major and minor seconds. But one way you could refer to this is say, he's filling in the chromatic collection. As opposed to if you saw a 12-tone piece, which is using all 12 pitches, but in a very specific way. Another scale Bartók likes is this one. I'm going to try to write it correctly. This is the octatonic scale. Half step, whole step, half step, whole step, half step, whole step, half step, whole step. Alternating half and whole steps. And this one you can actually refer to by a set theory name. You can call it the 0-1 octatonic. To say it's the octatonic scale that includes C and C sharp. And if you were to start the octatonic scale, on C, but start with a whole step and move from there. you'd get another octatonic scale that we might call 0, 2, because it starts with the whole step of C to D. There are additional octatonic collections you can have. If you start on D, you'll notice this is a different collection. No other scale has D and E natural in it, right? So this one we might call the 2, 4 octatonic scale. So you can label scales in this way. Okay, that's the octatonic scale. 8 different pitches alternating whole and half step, or half and whole step. Sort of related to that is the hexatonic. Which is sort of similar. The hexatonic scale alternates minor thirds and half steps. It only has 6 steps to it. And of course there's several versions of that you can write as well. You can start with the half step instead. And again, we could call this a 0, 3, call this a 0, 1 hexatonic. All right, that's another hexatonic scale. 0, 3, 0, 1. And these are symmetrical scales. Yeah, make some more room here. Symmetrical scales. So if we were to make our little clock face, someone on the street just noticed the dog. Okay, if we were to make a clock face and we were to sort of put a dot next to 0, 3, 4, 7, 8, is that right? 11. You would see you have this sort of symmetrical division of the octave. Same is true for octatonic. Right? This is what led Messiaen to call these scales and others he invented is way too strong a word, formalized, modes of limited transposition. Modes of limited transposition. These include hexatonic, octatonic, and then a bunch more that he sort of gave names to. Also includes everyone's favorite, the whole tone scale, which is also a symmetrical scale. This we would call 0, 2 whole tone scale. Or if you like, we could start on C sharp. And we could get the 1, 3 whole tone scale. Right. And these are the only versions of the whole tone scale you can make. You can only make the version that has a C in it and the version that has a C sharp in it.
you can't transpose this to another place that will give you a different collection of pitches. You either have this set of pitches or this set of pitches. And that's what Messiaen means by limited transposition. Unlike a major or minor scale, C major, you can transpose that many times and it has a different collection of pitches. But whole tone, you can only transpose twice. If you try to transpose it, say to, if you start on D, you just get the same collection of pitches. If you start on E flat instead of D sharp, you just get an enharmonic version of the same scale. Okay. So these are just some, certainly not all, of scalar collections, many of which the chromatic scale, the octatonic scale, the hexatonic scale, the whole tone scale, and Messiaen's modes of limited transposition that you can look up online if you're interested in those, or if you're analyzing Messiaen, you may be using them. All of these scales are what we call symmetrical. If we're analyzing Debussy, Bartók, Messiaen, they're likely to come up, as well as other composers, of course. Okay, I'm going to maybe look at some repertoire for briefly, and then we'll be done with this video.
Okay, so I just wanted to, oh, there's the dog. Dog shot, looking out the window, keeping us safe. All right. Just wanted to look at a couple of pieces quickly to think about scalar collections. Debussy, piano piece. Here's an interesting example. If you look at the pitches in this first section here with these trills, as you can see, there's sharps and flats, A major key signature, but this doesn't look necessarily like A major. What the hell's going on? If you start to sort of count up the pitches, C sharp, D sharp, C natural, B natural, G natural, B flat, A natural, F sharp, F, A flat. It's this sort of weird chromatic collection. But it's worth trying to fit it into a logical scale. So if you think, okay, C sharp clearly important. D sharp is also happening during this trill. So C sharp and D sharp. And my high point, we've got G and F. Okay, those seem important. We hit B a couple times. We've got A here. We've got G here and here. Okay. And all of those pitches make a whole tone scale. G, A, where's A? B, C sharp, D sharp, F, G. And we're leaving out a couple pitches. We're leaving out C, we're leaving out B flat, and we're leaving out A flat. But all of those are sort of operating the same way. They're all kind of like buddy, they're going down, sort of resolving down to something. Ba-da-dee-da-dee-da-dee-da-da, right? And so we're coming up with a principled way of removing some pitches here, saying these are non-chord tones, and this fits into a whole tone space. Right? Sort of taking cues from important pitches that are long. Taking cues from bars like this, C sharp, B, A, G, F, D sharp, C sharp. We get the whole tone scale there, presented very clearly. G, B, A, F. This whole bar is perfectly whole tone, right? So we start to get a clearer picture of okay, the whole tone scale is being used here. Which whole tone scale is it? It's the one with C sharp in it. People use different nomenclature for this. But you could label this on a score as just 1, 3, whole tone 1, 3, to say it's got C sharp and D sharp in it. That's how it starts. And that could be your label. And you could refer to it that way in a paper. When we get to this part, it starts to look a little more chordy. you start to see that A seems like an important note. We have A and E. We get a lot of this A and C sharp. Looks like A major-ish stuff. A major-ish stuff. Oh, there's a D sharp. Oh, there's a D sharp. There's a D sharp. Maybe we would call this, it's like A major but has a raised fourth sometimes. It's like A Lydian. Okay? And so again, thinking of this in terms of scalar collections, we'd label this A Lydian. Now of course, I'm ignoring that G natural, you may have noticed, right? I'm ignoring that G natural. And maybe that will ultimately be wrong, but we do get G sharps as well. And we get D naturals too. So, you'd have to make a case that this is A Lydian and not say A Mixolydian. Okay. In any case, that's what that would look like. And it may be there's not much more for these two bars to say as far as pitch content goes, other than this is A Lydian, right? It's not like there's chords that are changing. It's a scalar collection that's being used, right? Remember this little Bartók violin duet? We talked about it in terms of in a few ways, but we noticed the odd patterns in this piece. But one thing you can always do, especially with some of these early 20th century composers who are not working in a tonal idiom, is that we just start counting up what pitches we have. Well, this top line has A, B, C, D, and this bottom line has G sharp, F sharp, E, D sharp, E sharp, D sharp. And if you put those all together into a scale, you'd get like D sharp, E sharp, F sharp, G sharp, A, B, C, D, D sharp, which would mean like D sharp, up a whole step to E sharp, E sharp, up a half step to F sharp, up a whole step to G sharp, up a half step to A, up a whole step to B, up a half step to C, up a whole step to D, up a half step to D sharp. That's an octatonic collection here. So there are many things you could say about this piece and the various symmetries, and we talked about all of that in class, whenever that was, weeks ago. But another thing we could say is label this as an octatonic scale. Oftentimes this is labeled as oct, and then we could say, well, this is 3, 5, because there's no real maybe principled way to say where it starts. I'm saying it starts on D sharp and goes to E. If you like, you could call it C, D, so like 0, 2, just to start from the sort of low, the lowest number on your clock face. So we have a C natural and a D natural. Those are our first two pitches. So we could label this as octatonic too. And then we could look, oh, we've got 4 more pitches. D, E, F, G. Those are alternating whole step, half step, whole step. These 4 pitches are also alternating. I bet you anything. Whole step, half step, whole step. Right? And this would be a different octatonic collection. This one has a C sharp and a D natural. So this one we could call octatonic 1, 2. So we move from octatonic 0, 2 in this line to octatonic 1, 2 in this line. These 2 lines, right? And so on. So that's an example of finding scalar collections and labeling them in a piece of music. That's something you can do on your pitch notation annotated score part. Especially if you're struggling, like I don't have harmony to deal with. Right? This is totally contrapuntal. There's no harmonies to talk about here. But you can still say something meaningful about the pitch collections that are being used. You could also go a little further and say that this top line is using, if we start on A, 0, 2, 3, 5, and this bottom line, if we start on D sharp, 0, 1, 2, 3, 4, 5 as well. And so this is the octatonic scale split into two equivalent pitch class sets, prime forms, right? These are their prime forms. Their actual pitch class sets would be like, A would be what, 9, 11, 2, and no, 9, 11, 0, and 2. Is that right? And this one would be, the pitch class set would be D sharp would be 3, E sharp would be 5, F sharp would be 6, and G sharp would be 8. I believe that's right. So they have different pitch class sets. They form a single octatonic scale, scalar collection, but they have the same prime form. So that's a lot to say about pitch right there, without any recourse to tonal harmony tools. Okay, that's all I wanted to show you. Hope that helps. Let me know if you have any questions. Thanks.